Okay, I handed out the sign-in sheet, so everybody should get a chance to just sign in. And today, for the seminar, we're going to have Dan Fry speaking. And he is one of our adjunct faculty. You guys obviously can tell that there was some extra credit going around for people in his class to show up to. And he taught the radiation biology course last semester. He's also he works with Lockheed and works with the radiation group over there. And this semester he's teaching the statistical mechanics course, and he's also going to be teaching math methods next fall for me. So he's going to be giving a talk. He gave this earlier in the semester in Semina's Science Seminar Series about different types of particles, and I guess I'll let him explain.
Thank you. Well, I'm going to talk to you a little bit about, this is a little bit of a modification from the talk I gave earlier, where it goes more into detail of some of the physics processes when you're dealing with these particle suspensions. So I was about to head up here, and my daughter had found this that she hadn't played with in probably a couple of years. And I was able to coerce her into letting me borrow it. And because everyone's familiar with this, we've played with these since we're little, and it's a perfect example of a particle suspension. Shake it, turbulent motion mixes them up, gravity causes them to sediment back out. So obviously I'm not going to talk about snow blowing, but it kind of gives us a mental picture of what we're dealing with here. So what I want to talk specifically about is more of polymeric solutions. In particular, some nanotube work that I did in polymeric solutions, and how we handle the complex nature of the interactions and the behavior that we observe. So these things are everywhere. There's no doubt about it. Everywhere you look, there's another example of particulate suspension. Technologically, there's a lot of work being gone on. This is one that I thought was quite interesting. So this is metal nanoparticles that have actually aggregated up. The bar here is 10 microns in size. And in particular, what they're looking at here is they're actually using these nanoparticles for dispersal in inhalers for medical applications. So obviously, if this happens, it's not good for anybody. So that's one example of where these things show up. Probably a more personal example to everybody is what happens when you put some phospholipids in water. Okay? One of the things you get is, what I mean by a phospholipid is it's polymeric, but what separated it out is you actually have a hydrophilic head and a hydrophobic tail. Hydrophobic tail is water, and so if you put it in water, they self-arrange themselves in these structures. Now you can get a liposome, okay? So you can see now head, you've got tail to tail, or you can get a micelle where it leaves a little gap in here. More important, what I think is one of the more important things is actually this bilayer sheet, because that's actually the exact replica of the cellular membrane that all of us have in our bodies. The cellular membrane, as we know, is highly responsible for protecting the cells from viruses, amongst other things. So there's a lot of complexities that go into taking this already complex object, an ensemble of them, dumping them into water, and having them organized in this fashion. So this is another example of where some polymeric or nanoparticulates is in play. So in many cases, these systems are so complex that we have to devise some rather novel methods handling them. And one of the places that's good to start is you can actually look at relevant time, length, and energy scales of the system. I'm going to discuss a few of them in a minute. In many cases, you can actually prepare the system, meaning experimentally, you can prepare the system to be in one of those limiting case regimes, where you can limit now some of the complexities that you might see, understand something from the measurement. Most of the systems, like the examples I showed, the one I'm going to talk about, are highly nonlinear. What I mean by nonlinear is if I push on this table, it doesn't respond proportionally. So we have to think, if you think about something being nonlinear, you have to think geometrically. You have to think factors of 10 or logarithmically on how what that implies, and which relates back up here to the relevant time length and energy scales, that a lot of our observables are then power laws, then scaling to try and understand some global picture about these systems. Okay? So here's a few of the things that we worry about, or that we consider actually. When you're dealing with, you take the snow globe for instance, you have a fluid. Actually, I'll give you another example. Does everyone know what a dust bunny is? Right? So what's the fluid with the dust bunny? Air, right? And it's not a liquid, but a fluid can't sustain shear stress. So those things move around in the turbulent eddies as air circulates through the room and aggregate up. It's another example of particulate suspensions. In this guy, the water here has an intrinsic viscosity. The little essentially plastic pieces in here have a certain response time to move around in the fluid. Okay? And that's dictated by the viscosity of the fluid, another by the size of the particle. So what you have is, what I'm labeling here is an inertial response time. So you see the particle size, viscosity of the fluid, volume fraction of the fluid, depends on how much stuff is there. One of the big keys is KBT. KBT in all of these systems is essentially a universal scalar. It governs all of the interactions. So another characteristic time in these systems, as I'm going to show when you try and make these systems flow, is you have a turbulent time scale, which actually is dependent then on the dynamic viscosity divided by the density to power. And this epsilon, which is a characteristic energy of little eddies that go on in turbulent flow. In the polymer suspensions, and you know this from a rubber band, it's elastic. You have to do work on that rubber band to stretch it out, and if you let it go, it's going to snap back. So there is an elastic response time of the fluid that you're suspending particulates in, and that is proportional to the density of the solvent divided by the temperature squared. I note here that this is approximate because there are some deviations depending on what type of solvent you're using. The characteristic flow time is, in the case of simple shear, which is what I'm going to discuss, is 1 over the shear rate. And the diffusive, keep in mind now, with nanotubes, carbon nanotubes, you don't have a sphere, but you now have a pseudo-rigid rod. Okay? So these things undergo rotational diffusion in the fluid. So the characteristic rotational time is given by 1 over the rotational diffusion coefficient. This expression for the rotational diffusion coefficient comes from a very simple classical argument that was developed by Doi and Edwards about 2 decades ago. And it's simply just, if you can imagine a hypothetical tube that's surrounding this rod, all they looked at is essentially the overlap of when this tube rotates in and out of that constrained cylinder. You can derive an expression then that has the viscosity, the length of the tube, aspect ratio, the length to diameter ratio, ABT. So what we have then a tendency to do in the lab is we say, well, you know, we're going to throw, let's say we have a polymeric suspension, we're going to throw a solvent, we're going to throw a bunch of nanotubes in. Nanotubes interact with one another. Solvent has its own properties, so how do we actually limit cases to understand some universal property about this system? And it comes into play where you consider limiting cases where maybe the elastic time response is long compared to the inertial response time, vice versa. Or, for instance, if you had relatively lamellar flow, it's not very turbulent whatsoever. The characteristic to turbulent time is very strong, and the inertial time response time might be very small. You might have particles that settle out. And so by playing this game back and forth with how you set up the experiment, you can force the system to go into one regime, and you can see if it behaves how you want. So all of these guys, whether it's tubes, spherical particles, individual micelles, they go in a solution and they interact. They have some interaction between them that's directed along their centers. And in many cases, you can model it as what's called a diffuse double layer interaction. What I mean, the gist of this is that if you put them in water, for instance, okay, we know in water you have the H2O separates them and you now have ions, okay? Put a metallic, let's say it's a metallic gold nanoparticle in solution. It's got a surface charge on it. And those ions end up coming up and interact with that surface charge. And it creates this layer of charge around them. It tends to shield them from one another. So what you can do is you can add a little bit of sodium salt that tends to now decrease the ion concentration around the spheres. And then the spheres tend to aggregate very fast and they'll form clusters in solution. So notice the scaling factor again here, the way I plotted this is KB. Everything here essentially is governed by KB. The intensity of this, in other words, this is sitting at 7 KB. This one's sitting at 11 KB. So that gives us a range of what? It gives us an idea of how strong they interact compared to their thermal motion in solution. Because KB is dictating how much they diffuse around. Cool it, they have very little diffusive motion, and the interaction can take over and form together. Does that, you end up having now phase separation. It's govern the behavior of the system by changing. This was actually this was for a specific system. This axis here is in nanometers. All these constants, you see this reaction constant is 30 millivolts. A was 50 nanometers. So this was for a specific system for different concentrations of sodium salt, which you can see changes the interaction potential. As you increase the sodium, this repulsive barrier, which would keep the particles apart, gradually lowers. And so aggregate here. Now, one important thing where scaling, immediately we see scaling is if you limited this to spherical particles, you add in some salt, they would aggregate together, and they form these branch structures that eventually span the system. The nearest neighbor separation, the separation between two clusters of particles in the system, divided by their characteristic size, is a power law in time. This is how it grows. But notice, little d is the space dimension. Z here turns out to be roughly 1. EF is a fractal dimension because they grow as fractal aggregates. So immediately, from very simplified arguments, we get a scaling law that's nonlinear. This exponent is less than 1. So let's go on to the system that we actually want to look at. These polymeric solutions are very hard to make them Brownian and not to be Brownian. What I mean by Brownian is KBT is governing their motion. Is around in solution. But we can somewhat control the nature of how Brownian they are by looking at how much tubes we put in per unit volume, the flow velocity, the shear rate, which I'm going to come back to in a minute. And we characterize this with the Reynolds number. The elastic contribution from the suspended medium. So how viscoelastic is the polymer solution? High molecular weight polymer suspensions can be made viscoelastic, and in many cases they're non-Newtonian. What I mean by non-Newtonian is if I had, you can consider a block of water, apply a shear stress. Okay? The deformation is proportional to how much I push on them, how much shear stress. For non-Newtonian fluids, that's not the case. This stress is not equal to their viscosity times the shear rate. So the response is not proportional to how hard you push. So let's look at some of the characteristics that we studied. What I've broken off here in two boxes is, go to this side. First, we looked at two cases. One was single-wall carbon nanotubes and one was multi-wall. Multi-walled, essentially, if you think of it as a graphite sheet, multi-walled is if you rolled up the sheet and you had multiple layers. Understand what I mean? Multi-walled, you could have it doesn't close back in on itself. Single-walled, pretty close. It doesn't quite, but it's pretty close. Single-walled are typically, as you can see here, single-walled are typically much smaller. This is not millimeters, that's supposed to microns. Their orders of magnitude shorter in length and typically an order of magnitude less in diameter. And likewise, then the aspect ratio, because it's not quite 1-to-1, the aspect ratio is a little different compared to. Multi-wall tubes are easier to work with because of their size, you can use more standard microscopy techniques to look at them. Single-wall nanotubes are a bit trickier, and oftentimes you have to use neutron scattering in the actual study. So we covered here a range of what I call the phase space of the system. So what I plotted here is this Peclet number. This Peclet number is a ratio of the flow rate of the solution divided by this rotational diffusion coefficient. So if you imagine that Peclet number, it's at small Peclet number, the rotational diffusion constant is very big, and the flow rate might be very small. To go up in Peclet number, that could be analogous then to having a very fast flow. So that's how we're governing the system back and forth. So this is the range of the phase space for multi-walled. This is the range for single-walled nanotubes. And I'll mention a little bit more about the Particulate number in a minute. It becomes very important for what we wanted to do. This polymer suspension was polyisobutylene. And what we did was we took either 500 or 800 molecular weight and we mixed it with a very small fraction of a 10 to the 6 molecular weight, which made this what's called a Boger fluid. And what it means is that it's both elastic and it has a constant viscosity over a wide range of shear rates. So how do we actually define some of the limiting behavior? The most convenient thing is to look at things in terms of dimensional scaling parameters. So, and one of the reasons is we can set up the experiment in a way that we force it to be in a certain regime. We can control these parameters in general if we pick our system carefully. So one of these is what's defined as a Stokes number. It's just the ratio of the particle response, that inertial response, to the turbulent response. So what I mean by that is that if you imagine in a very turbulent flow where this characteristic turbulent time is very small, this Stokes number becomes very large. Reynolds number is the ratio of inertial to viscous forces of the suspending medium. So in this case, it would be of the polymer solution. So you see a dependence here on, for the geometry I'm going to talk about, which was just two parallel plates, one which was rotating, simple shear flow. L is the plate separation, and we have the density of the polymer suspension divided by the viscosity. The Weisenberg, notice that on none of these so far have I taken into account the elasticity of the polymer suspension. That's typically done with what's defined as the Weisenberg number, which is a ratio of the flow rate to the elastic relaxation time. So if you applied a stretch to these polymers, the question is, and then you let it go, how much time does it take for it to relax back into its heat? So you can imagine that has some effect on how this suspension flows. And of course, the flow rate comes in through the gamma. So this rotational Particulate number, as I mentioned, is just defined as the characteristic flow time. I just noticed this should be underneath. It should be 1 over gamma dr. The characteristic flow time to the rotational time, which is given by this rotational diffusion flow. What we've witnessed a lot of times in these suspensions with multi-walled tubes is that even though you have a simple shear going on, and then you have a velocity profile. What I mean by that is that I have a top plate that I'm moving, and the bottom plate is held fixed. So if I looked at the velocity profile, it would be like this. Okay? So this is a simple shear geometry. So in many cases, what we find is that you can watch these tubes under the microscope in the shear cell, and they will just kind of slowly, depending on the shear, kind of flip back and forth. Sometimes it'll be moving along rather steady, and there's so there is some rotational diffusion. So how do we actually look at this? Well, light scattering is the prime method. So remember your geometric optics. What determines whether you can see it essentially is comparing the characteristic size of the system to the wavelength of light. So in these cases, for small angle light scattering, we're able to use light that was roughly in the order of 650 nanometers to probe multi-walled nanotubes. Single-walled nanotubes are very, very hard, simply because we don't have a small enough wavelength. The Q value, this Q value is actually our measurable. That's what we end up going and measuring in the lab. We keep lambda fixed, and we look at scattering as a function of theta. And that tells us something about the characteristic length scales in the system. So it could be something about just the size of the tube. It could be something about the size of the cluster as these tubes aggregate together. It could be something about the size of the domain if it starts undergoing phase separation because of polymer. Those things would show up in the light scattering patterns. Another one that's turned out to be much more beneficial than we thought it was, and we essentially, this work was done at NIST in Maryland. We had to resurrect an old apparatus. It was in a way, it was done in a way that we didn't really want to do it, and we didn't think it was going to turn out anything. But the idea is that this system, because these tubes can align in the flow, and the tubes have an aspect ratio, think about absorption of light. It has a greater ability to absorb light that's polarized with the electric field in this way than it does transverse. Simply because the electrons are more free to move on axis than they are across. So the idea we had is that we might be able to measure the birefringence, or the scattering dichroism, which is an orientation-dependent absorption, and learn something about how these tubes are flow aligned. So here's the setup. We had a helium-neon laser that's roughly 650 nanometers. Turns out to be that's H-nu is about 1.6 dB. We could pick the polarization to be along, what I've defined here is this is the flow direction, the direction of the velocity vector. Perpendicular to that is a vorticity direction. So we could decide whether this whether we were flow aligned or not with the polarization that we picked. This light could then be scattered. The sample was held in here. These were two quartz plates. The top one was rotated at a given frequency. Light was scattered then off another 90-degree mirror. Measure it here. The other thing we could do is we could actually shine white light through this cell, and we actually could pick it up also on the CCD camera, or that with the VHS recorder. It gave us the ability to probe it with just white light and look at it optically. But we were limited on how thick the sample could be, because if we couldn't get enough transmitted intensity through here, we wouldn't be able to see anything. And the thicknesses between these plates typically range 200 microns. So the second thing that we did is, you might imagine now, if you take this polarization, remember the polarization vector is essentially, in this case, would be one direction, the other. If you fix the direction the electric field's oscillating. If you modulate that and you allow it to rotate, now you can pick out, as if you average over time, you can pick out if the tubes are aligned in this direction. That's the hallmark of doing flow birefringence, the same with dichroism. So what we did is we modulated also the polarization vector of this incoming beam and also captured it. What you see up here is just an example of some of the patterns. What's listed at the top, this is 2 inverse seconds, 58 inverse seconds, 9400. This is increasing shear rate. So what you see is a striped pattern here. What this corresponds to is that, think of a dipole, right? You have, if you think of these things as a dipole, scattered intensity is greatest 90 degrees to the way the dipole is pointing. Okay? So in this case, the gradient axis is z. X is the flow direction. And so if they're flow aligned, you get more intensity in this band. So what we looked for we looked for how wide this stripe was, or whether it was bulging out to the side. And that gave us a measure of how flow aligned these tubes were, whether they were all pointing up in the flow direction or whether they were randomly oriented. So this is an example of a system. I wanted to show you how you would extract from a light scattering measurement something about the characteristic size of the system and how it's behaving. So what I've plotted here is, this is S of Q. S of Q is the structure factor, which is related to the scattered light intensity by just multiplying by n, the number of scattering centers you have. In this case, it would be the number of tubes you had in suspension. This was a measurement that we did at K-State. This was actually taking an acetylene diffusion flame. We just had a burner sitting on a table and shining a laser beam through it at different heights. So if you look low in the flame, you have a lot of small soot particles. As they move up through the flame, they actually aggregate and they form fractal aggregates. And they get bigger and bigger. So simply moving the laser to different heights, you're mapping out the growth in time as these things move. Here's what we see. We actually see two power laws. One with an exponent of minus 1.8 and one of an exponent of minus 2.6. And you see a bend here. Now, any place that you would see a bend in the structure factor is a characteristic size. Remember, Q is 1 over length. Okay? So clearly there's some difference here between the growth in this regime where up to this characteristic size. The system then changes over into a new growth. Turns out actually that these numbers that it fits remarkably well match the fractal dimension for diffusion limited aggregation percolation clusters. So just by looking at the light scattering patterns and looking at the power law, which is inherently then nonlinear here because it doesn't have a slope of 1, you're learning something about how this system is evolving and what structures are developing inside. So what do we actually see when we shear the polymeric suspension with carbon nanotubes? Well, what I've got here is one of the microscope images. And what you can see, you can make out few individual tubes in the shadows, but for the most part, they've actually clustered up. Tubes themselves have relatively strong interparticle interaction between them. Just push on them a little bit. Now, you got to think about this for a minute. This polymer suspension is highly viscoelastic. The actual, not the rotational, but the actual translational diffusion time is very long. So if you don't give them a nudge, they don't tend to go anywhere. So if you put shear on a little bit, you wait a couple of hours, you actually can see these things start to flood, or they aggregate into clusters. And what I've got here is a simulation result. This was actually a diffusion limited simulation where these spheres can only move around under their own diffusion, aggregate together, and they form this branch fractal aggregate. So there is some resemblance between this structure, these flocked tubes. The difference on these, if you notice, is you can see how black they are. They're relatively compact. Okay? And it has a lot to do with the viscoelastic nature of the fluid. Tubes tend to come together, and they kind of tend to torque about an interaction point. Notice that their high aspect ratio. If they touch, they're going to touch in one location. So that has a large impact on how compact these clusters turn out to be. Now, if we push on it hard enough, if we increase the shear rate, we see that we tend to break them back up and redisperse the nanotubes. There's a regime, there's a phase transition you go through that, as a function of shear rate, that we can control to disperse the tubes in suspension or have them aggregate up back up. Another interesting phenomenon that we saw that was completely unexpected is that, well, let's look at it here. These are light scattering patterns, okay? So what we did here is we pushed on these tubes at a moderate shear rate. So what you're looking at here is the different degrees, whether we measure horizontal polarization, vertical polarization, as a function of time. So this is increasing time. If you notice this system, it's relatively, there's a little bit, maybe a little bit of a bulge, but here in HH pattern, which measures the flow direction, it's pretty much striped, and we could see it that it was relatively flow aligned. After we waited a while, and this was out to 19 minutes, we noticed that it was developing an equal sized bulge in this direction as in that direction. Now, if everything that was, all the intensity vertical had gone horizontal, your particles, your tubes would go from flow aligned to essentially vorticity aligned. But there's clearly some separation of orientation here. But what we saw was that if you took the quartz plates and you started to squeeze them so that you could run the plates up and down in the sample. And so you could see the distribution of tubes at the surface of the plate. It actually turned out that there was a length or a size segregation in the tubes. The big tubes were dispersed more in the gap between the plates. The smaller tubes had aligned themselves close up to the plate surfaces. The way you can imagine it happening is that you can imagine in a big system, if the plates were orders of magnitude separation bigger than the tube length, then all the tubes have all of the phase space to wander around in. But as you start closing this gap and you start approaching the length of the tube, the longer tubes, they don't want to come in close contact with the plates. They tend to be more flow aligned. And so it squeezes out the smaller tubes and they tend to go towards the plates. And we don't know exactly why it happened. That's more of a geometric argument. That's what we think was going on in the system. One of the reasons we're interested in this is because you want to use nanotubes to impregnate plastics or other materials to reinforce their characteristics. You need to have tubes that you would like to have a monodispersed distribution in size. You'd like to have all of them the same size. You just can't get it. So if you could size segregate through some processing scheme where you force these tubes through a shear cell, maybe you could separate them out and purify the system. So you could separate tubes into one size. That's why we had gotten interested in this after we saw it. The other thing we saw likewise was that not only did we have smaller tubes, but if you looked at the smaller tubes, they tend to be more aligned in the vorticity direction, flow direction. Something that we still don't quite understand exactly why. We think it has something to do with the elastic nature of the polymeric suspension. Because what happens is as you try to, if you think of this flow cell moving around, you have a velocity gradient that's oriented in this direction. You actually, in that case, it has an effect on the polymer suspension that you're trying to stretch it out. But that changes as you go along the vorticity axis. And so we think there might be an effect there that's causing the bigger tubes that would have more of that stretching would have a bigger impact on the larger tubes than the small ones. And maybe that's why we see an orientation degradation here. You can see it here. If we took some of these micrographs and we looked at the number density as a function of angle, the tilt angle. And so this is in the bulk, okay? And this is actually close to the wall. And so you actually see at 90 degrees, this is 90 degrees to the flow direction. So what do we see if we look at the optical properties via birefringence and dichroism? What I plotted here, there's a lot in this graph. So let me take a couple steps here. What I plotted here is delta n prime is the birefringence divided by phi, which is the concentration of tubes. Delta n double prime is the dichroism. It's the absorption of the incident light by the tube. What I plotted here is this Peclet number, again, which is the ratio of the characteristic flow time divided by the rotational diffusion time. Essentially, how quickly they can rotate in the flow compared to how fast. What we did is we took a whole host of different concentrations that you see listed here. The M1s and the M2 comprise multi-walled tubes that have slightly different solution properties. In other words, a little bit different than the molecular weight of the polymer. The S's are all single-walled nanotubes. Now, one thing you might expect from this system is that if you consider the rotational between, just look at single-walled to multi-walled, there's a huge difference in the aspect ratio. The rotational diffusion coefficient is different. So you might expect that if you just plotted it versus rotational diffusion, you get data that was disparate. They were separated by some distance on the horizontal axis. The utility of rescaling everything with Peclet number is you accommodate for that. Because now you're scaling this with respect to the flow field and accommodating for its own difference in rotary diffusion. When we did that, we saw that all of the data we had, for the most part, collapsed onto a common curve. So this simple model that Doi and Edwards developed of just a rigid rod polymer, the rotational diffusion coefficient, seems to work for a whole class of conditions here for nanotubes and polymer suspensions. Look at the range also on this Peclet number. I mean, we had data down to less than 1 all the way up to 10 to the 10th. There's a very large range here covering, these were essentially Brownian suspensions. These were highly non-Brownian suspensions. Now, there is a difference in slope, but again, we still get a collapse of all of this data. So this tells us something about how you can, the point of this is that to look at the optical properties, which is what we really wanted to understand about the carbon nanotubes, you can vary a lot of the parameter space in the properties of the suspensions to extract that information out, regardless of the size of the tube, regardless of the type of polymer suspension you have, regardless of the concentration. The other thing we did, and this was a little bit, another thing that was a bit surprising to us. Think about, you know that kids game with pixie sticks? And you drop them and they fall all over the place? So the tubes, if you think about it, the tubes, if you crank up the concentration of nanotubes, you have a bunch of rods and a lot of them are overlapping. Now these carbon nanotubes are known to have a very, very high tensile strength. Okay? They're incredibly hard to bend. So they're not going to flex if you push one up against the other. Right? The idea we had was that let's sit here. So what I plotted is the viscosity versus the deformation. So we had parallel plate geometry. We wanted to rotate the top plate with this multi-walled suspension in between, measure the viscosity. What we see is that for both of these concentrations, what happens is the viscosity initially looks like it's diverging. So let me point out here, this 1 plus means it was the first pass and we're going in the positive direction. The 1 minus means we stopped and then we rotated it. 2 plus means we did it again and then came back, and the 3 plus and so on. What you see, now think about just a shear stress here. A fluid, we know, it can withstand no shear stresses. You push on it with an infinitesimally small force, it deforms. Concept of a yield stress is that any substance it will resist that force you put on it up to a certain limit, and then it'll flow. And that's actually what we see. What we find here is that initially the system jams. The viscosity goes through the roof, all the tubes lock up, and the system just stops moving. Reverse it. Now that's a yield stress. Initially it starts to flow, and then it stops. The system jams, develops a yield stress. But if you reverse it and you cycle that back a few times, you essentially take all of these crossed rods and you kind of wiggle them around until they're somewhat aligned in the system. So it's, again, these concentrations, 3 and 6%, the sample was black. You could not see through it for quite a bit of tubes. One of the last things that we looked at was, instead of now, we essentially wanted to go back and look at, as you vary the shear rate, but for lower shear rates, where we might let the system sit for 6 hours, 12 hours a day, what happens to the system? So there's a lot in this picture. What we find is that if you look at C and D here, these are just two different contrasted images to kind of highlight. Below some critical shear stress, there isn't enough energy to, the tubes come together, they aggregate, and there isn't enough energy in the flow field to break them back apart. So what happens is you develop little clustered regions. The reason you get a banding, this banding show up is that you can see small aggregates out here. The larger aggregates just eat them up. It immediately starts forming depletion regions, and there's a greater propensity for these small aggregates to go towards those bigger regions. Form this banding structure here that happens to be aligned with the vorticity direction. The other thing we found was, if you looked at light scattering of some of these regimes, we did find, again, this is structure factor versus Q. So this is inverse length scale. So in other words, large Q is small length scale, small q is big length scale. So the system size is out here somewhere. Tube size is back here. But what we find is we find two power laws. And sure enough, this large domain power law, in other words, what it looks like across this entire band, almost looks like percolation, fractal dimension of the tube. So inside, that's across the whole thing. Inside, there are smaller aggregates that have a smaller fractal dimension. The domains are characterized by a different structure. So where can we apply some of these things? There's a few places that I think are very, very interesting. A lot of them have more to do with the medical and biological applications. One of the ideas that's out there is these magnetic viruses, and I think it's very interesting because what they do is the idea is that you remove the virus entirely remove the DNA from the virus material. You actually, and all the materials where you actually create this shell that you can now backfill ferrous oxide type of particle. You can track in the body. You can now conjugate the outer casing of this to target specific types of maybe body. That's part of the same concept of this biohazard detoxification, but there what you're going to carry is the surface of these nanospheres. The nanospheres here could be metallic, or they could be something like this, like the polylactic glycolic acid. You have surface receptors actually that go now and will target specific invaders in blood. Now all of these systems though, we have to keep in mind that in order to really push this to be able to be used, there have to be studies done where these particles are immersed now in a suspension that is similar to the blood. And the blood, as we know from the platelets, red blood cells, is highly viscoelastic. Not to mention turbulent, depending on where you are in the body. So there's a lot of work to be done there. This one I think is much kind of more interesting to me, the idea that you can actually take a nanoparticle of a shell and you actually can inject whatever medicine that you would want in it and now inject this into the body. And that's one example was the delivery of contents for stroke victims. It's a very big time sensitivity. Shortly after the stroke, you've got to get it taken fast. So this is just a couple examples. Let me just acknowledge a couple of people here. A lot of this work was done, some of it was done in Kansas State, a lot of it was done in NIST with Derek Cobby and Bang Langhorst, Howard Wayne gave us a hand. Eric Roque supplied all the nanotubes that we use.
Hey, questions? Yeah.
You are talking about nanotubes. If I consider this as a modification from spherical shape to the cylindrical shape, has anybody looked at the situation where instead of cylindrical shape, it flattened out like a disc type of shape?
If the tube itself, the same properties,
Yes.
or are you relating back to the applications?
No, I'm relating to the applications.
No, and that's, you are related to applications, you said. Okay, so there's a few things here. There's not a lot of work that's been done on varying the anisotropy of the particle shape, how fat or long it is, or whether it's smooshed out like a disc. There hasn't been a lot of work on that. Spherical particles have been the mainstay just because they're easy to make, they're easy to get, the interactions are very simple. If you have something that's oblate, trying to calculate the interaction to that is much more complicated. I think there's some work that's being done just with red blood cells in suspension. And I know there's been quite a few simulations of that, which are disc shaped. Well, they got some concavity to increase the surface area. But there's been a lot of simulations done on how they aggregate in the blood and how they might interact with other invaders. But I haven't gotten into any work on
I
it.
think it might not be possible experimentally, but probably theoretically, models like in computer simulation. I'm not sure, but that is comparatively easier as compared to having really,
Yeah, well, definitely, and probably in the simulation it's easy. But one thing that another guy at NIST is working on, I mean, if you looked at an emulsion, right? An emulsion is a particulate suspension, but there you have two different phases of liquid. So essentially you have a background, and then you might have some type of droplets. These could be oil. There could be a host of things. It could be micelles, for instance. These also, because they're elastic, they can't sustain much of a shear stress, and they tend to deform. So what happens there is you tend to shear the system, and you tend to push them into a state like this. So what you might be able to do experimentally is you might be able to take an emulsion where you have micelles or liquid droplets and force it into a state where they're shaped like this at a fixed shear rate, then study the system in that state.
So just like changing the constraints and
Right. The problem comes in is how you make these to actually go study them. Right? I mean, it's somewhat a manufacturing problem. How do you make something that's oblate or that's disc-like? But this is probably, you could do this fairly easy. Steve Hudson at NIST is doing some work with this.
Now, this is essentially a study nanoparticles in suspension. How do you compare? You mentioned something, the hydrophobic properties of natural things,
Yeah.
which can change everything somewhat.
Right.
I mean, in a nanoparticle situation, you've got a fixed chemistry, which is pure chemistry. Is the next step somehow to modify the chemistry so you can manipulate the whole picture?
Well, that's a good point. And we actually, I probably didn't point it out there, but some of the single-wall nanotube work was with surfactant, and specifically for that purpose. We've also done a few studies with neutron scattering, small angle neutron scattering, where so the idea is that if you've got a tube in solution, and you actually can coat the tube somewhat with surfactant, and that surfactant then has the effect, just like you would have hydrophobic and hydrophilic, to end up. So these could be functional groups that are attached, that essentially make the tube fuzzy. Then they don't like to come together and you keep them dispersed. Surfactants seem to work okay. We still ended up getting little clumps of material, and it might have to do with just how well we were able to coat it. The other thing that we did, and there's a lot of work that Eric's group is still doing on that, and that was to actually wrap this in a single-stranded DNA. So the phosphate group tends to stick out. And this actually was able, with single-wall tubes, we were somewhat able to disperse them in suspension. but there's a lot of work that's going on using chromatography, column chromatography, to study this property and see if you can separate out by size. But that's all we had done with it. I think there's a lot of work that can be done and is being done on functionalizing the tubes, like you say, where you change the surface chemistry.
Because in nature, of course, in the bloodstream, you can't afford to have aggregations.
Right,
Proteins.
right, yeah, yeah.
Obviously, the blood works it out for itself somehow.
Right. No, and I think that's one of the big questions with putting magnetic nanoparticles, for instance, into the bloodstream for imaging. And one of the ways that it's proposed to do, and some people have done some studies with rodents, is to you coat it with polyethylene glycol, which is very biocompatible, and I think it has a similar property as a surfactant. It kind of tends the nanoparticles apart. But one of the hard things on doing things like that is you can propose a lot of different ways, and then trying to get it to work, now have to submit to different types of clinical testing. But I think it's interesting. I think there's a lot of application. The realm we're in, and I think we've been in really for a decade at least, is trying to take the properties of these complex systems and tailor them to do things we want. And it has a lot to do with modifying the chemistry. Question?
Yeah, I guess back a few slides back where you're talking about the smaller particles were in.
Yep.
Possible that they're similar scale to the big particles.
Definitely. And that's well. Okay. Let me say this. In these systems, I didn't mention it. The Reynolds number was low. The Reynolds, actually, I had it back. So you can see here the Reynolds number values. The biggest was 15. Maybe get to 2,300 to be turbulent. But that said, these are bulk properties. Clearly close to the plate. I don't know. There might be imperfections in the quartz that are causing the flow not to be laminar, and maybe you do have some eddies that spring up there. I don't know. But I can definitely see it as a possibility. I mean, these plates were optically polished, but you don't really know.
Your analogy with the blood cells. Actually, the blood, as it goes down to the capillaries, it actually necks down, so the red cells stack on top of each other and move like a stack of coins.
Huh.
And occasionally there'll be a white cell in there. And in fact, if you've ever seen spots in front of your eyes,
Yeah.
what you're actually seeing is the white cells interspersed in a chain. The little spots, the little dots that you're seeing are actually white cells that you're seeing in the retinal blood vessels.
That's really neat.
Yeah. But the thing about that is that the blood doesn't just flow in the veins, it flows, and so every time it circulates, it gets stacked and unstacked.
Huh.
And stacked and unstacked, because every time it goes to the capillaries, it stacks up like that.
What happens at a junction? I think that's the part that, and I think people have looked at that. The problem is what happens at a junction. Because here, I think what happens is you have problems with the flow being broken up somewhat. And the idea is that here you might be able to create, and of course, it can't be in the very, very small capillary. I mean, it's got to be something big enough to sustain an eddy. But some of the simulation work I've seen is that there's some tumbling that goes on here. Now, the idea, I think, too, is that once you get down to, if you want to use nanoparticles and you want to use something that crosses over the blood barrier, you need to go down to something that's like 6 nanometers. So now you're going to have, clearly you're going to have an interaction with the blood cells, but those things are small enough to kind of move around. It's almost like if you walked up, what I'm thinking of is kind of, not the best analogy, but if you walked up after, a jet flew overhead. And there's some wake in the flow that these little particles would get caught up in. And I think there would be a high propensity, just from what we see when we look at turbulent suspensions. In an ideal case, they'll get hung up in the eddies because they get trapped there, and then if they get trapped, they can aggregate. And here it would be a problem because you're at a critical juncture. But again, some of this is speculation based on what we've seen. I don't know, but I would definitely find the time. We'd like to like to look into it.
Is the nanoparticle work generally aiming for medical research or mostly other?
I think there's a lot of, I think there's a large portion of it that biotechnology, I think, has really scooped up probably a lot of the funding dollars in nanoparticle. But there's still a lot of fundamental studies going on because I forget, this was a couple years back, I had gone to one of the big journals and looked up all the papers that were published on nanoparticles, and it was just hundreds. There's a lot of funding into it, but the bottom line is that even after a decade or two of this mass push, because they offer much promise, we're still trying to figure out kind of what to do. It's not so clear cut. At NIST, Eric Hobby's group is looking at just the uptake of these tubes in cells. I mean, they grow cell cultures on a substrate and then look at how they uptake the nanotubes. They found for single-wall nanotubes, they go right in past the lipid bilayer. That could be very bad. I, for the life of me, can't imagine that you would want a carbon nanotube inside the cell. I don't think that would be good. But and so then you bring in all of these a lot of talk on health risks and things like that. One of the things we're talking about, even in our group at NASA, is that the problems with going back to the moon and lunar dust. It's a tremendous problem to figure out how much is going to be inhaled, how much will be trapped in the lungs, how much, and in those pieces, if you look at, I looked at some of the slides on them, of the cross-section through it, you can see a micron piece, and you see specks in it of black iron, just pure Fe, that are nanoscopic in size. I mean, they're anywhere from 5 to 10 nanometers. So now the question is that you put that big thing in the lung, and what's the chemistry that goes on that maybe erodes it until the iron nanoparticles come loose and cross over into the blood? No one knows. I mean, we don't. But I think we need to find out. So those are just some of the things I think people are looking at. Not enough time to invest.
I was just wondering that you were talking about size, of course, is different from mass. But if it is somehow related to, it is of course related to mass. So is there any technique like centrifuge kind of techniques which can be used to do segregation?
Well, there's a lot of, that's another thing they're doing at NIST, and they're doing it other places too. I mean, the idea is you do chromatography on a column. I mean, traditional gel chromatography, you can separate out sizes by passing the substance electrophoretically through a gel. And so there's some work that's being done where they adapted that concept to push a nanotube sample through. And, I think they get good results. The whole question is always not just whether you can do it, but how much time it takes to do it. Because if you want to put it into a processing application, you have to be able to do tons of it in a relatively short amount of time. And so if you can only make a gram of a pure sample in a day, I don't think anyone's going to do anything with it. So I don't know. That's a few of the things. And with this method, it's interesting. I'm not really sure that we could go anywhere with it. We still haven't quantized how much of it segregates out, and I think that's, with the current method that we have here, we can't do it that way.
There is another thing which is related to that. When we talk about composition, if you know that, so if there is an iron compound or things like that, is it possible that magnetic field could help or kind of segregate them in a way that it...
Yeah, that's something that I've been thinking about. The idea there is that you have a magnetic fluid. So you have, what I mean by magnetic fluid is really magnetic dispersion. So you can have magnetic nanoparticles in a dispersion, and when you put them in a magnetic field, they tend to line up. If the field's strong enough, the particles just stack. And so you'll find aggregates, and if the field's high enough and you put it in flow, you'll just have a bunch of spheres that have lined up. I don't know. Maybe you could disperse these magnetic nanoparticles in solution first, add in carbon nanotubes, shear them at a very high rate, so all the little beads are interdispersed, and then turn on a field. Maybe it would, if these line up in between tubes, then maybe it would separate out. My guess is that you would have to have
quite a large concentration of these guys compared to the tubes to fill all the gaps in between.
Probably it will also depend on the rubber fluid also.
Yeah.
Blood or other things.
Right. Well, I think we talked about it a little bit. You and I thought they talked about a little bit about that. Maybe I've been meaning to talk to you about it, and I just didn't get around to it yet. Yeah, actually, thanks for saying that, because I do want to talk to you about that afterwards. There's an idea I had about that. Okay.
Did they succeed in doing these virus, assembling these to the anode of the battery?
I think they have a template, but I don't think it's been tested. I think there's a template built they have a way of doing it, but it hasn't been tested in terms of its utility.
Virus themselves do cluster and assemble these stuff.
Yeah, well, let me back up for a minute. Some of them, what some people have done is take also already spherical particles and then conjugate it with a virus where there's a receptor on another bead. Watch them aggregate together. That's the hallmark of this, what people are looking at is binary colloids, because you can tailor the different size beads to come together. In that case, though, the template they have is, they actually take, I think, the capsid shell. They're able, and I can't tell you I know exactly how they do this, but they're able to essentially pull out the junk in between. Claim to be able to backfill it. I don't know exactly how to do that. I know you can do it with liposomes with optical tweezers. But you're doing it with one at a time. So I mean, if you need to have, as we know, 10 to the 23rd, have an ensemble.
When you do this work, do you purify the nanotubes to the nth degree? You have to, I guess, to study it probably. They have a little different property, do they not, when they're so purified?
Yeah.
They don't represent.
Well, the multi-walled tubes. So what we get, the multi-walled tubes are created with this, essentially a carbon furnace, this HIPCO process. And they come off, there is a distribution. I mean, what I'm listing here in terms of the length is the mean length. So what we found is that when we looked at the sample, I think it was log normal. And I don't remember the width. The width was probably about, I think, 5% of that mean length. It wasn't highly, we actually got them processed somewhat, that they were somewhat, the distribution was narrow. And then we use that sample. Now, you're asking whether that changes the...
How they interact.
Yeah, so what we would like to have is a completely monodispersed in tube length, right? We want to have all of them the same size. So then we can... So definitely, if there's a little bit of a disparity in size, that'll affect some of the properties. With the size segregation, when we saw it closer to the plate, initially what we thought we saw was that they were just oriented differently and it was a shadow. But as you close the gap on the plate, you actually could see the little ones in there actually moving as well. So we knew it wasn't a shadow. They were small tubes. And they were much smaller than the ones in the bulk. So I guess what I'm getting at is, now we don't know. We don't know exactly... If you've got a size distribution, that should be at 0. That should be somewhere here. So if this was essentially the mean length, we don't know. Did we have something out here?
Is it a calcium distribution?
Well, not quite. It's more. It's more log normal than it is calcium. But that's something we didn't have a way of actually quantifying. The exact number, because in order to see them, we had to scan the plate up and down. So as you moved, you lost some of the ones that were in view. I don't know. We have to devise another way of looking at it, I think.
My name's Alex Munchak. I'm taking this course as a continuing education
Yeah.
student. But one of the things in the class is to understand how things are published.
Yeah.
You mentioned journals and also, where would you publish this kind of research, and what journals have you looked into?
So-
Also for JSC, is there one place where they publish all of the human space exploration?
Well, one thing I'll say, and this isn't I'm not trying to get on JSC, but I wouldn't look at their center for publications. They just don't. The things they have are in terms of journals for this work, are kind of few and far between. But if you go through the university, all of this work is published. So all the work that we did on on this, with these systems, I don't remember, this one I think, that one's I think Lane here, but all of this work here, if you go to physical review letters, you can search Eric Hobby, you can search my name with nanotubes, it should come up. We published it also in chemical physics letters. We published it in, maybe it's just Journal of Chemical Physics also. You might look in Langmuir also. There's a few things I've published in Langmuir that deal with colloids. But if you go to their website, you go to Physical Review website, it's all there. These graphs here are taken out of the articles. Yeah.
So back to the alignment.
Yeah.
How much of the alignment was a result of
That we actually think close to the plates it's strong. That's the idea. Is it's maybe just a geometric crowding. If you get a plate that's separated by like this much and you're trying to fit a tube in it, you just can't. It needs to fit this way. So there's some geometric, because we had to squeeze this down in order to see the smaller tubes. We don't know. Maybe we forced it to some degree also to be like that. I don't think so, because as you backed off, we knew the plate gap, and we could measure from the microscope how big the tubes were. And in general, we were an order of magnitude longer than the tubes. So something else was going on. The gap, we don't think, was confining it. Maybe there's something at the flow. I don't think it was an interaction between the tubes, because in the systems where we saw it, these systems aren't very dense. So the tube interaction should be much weaker there. Yeah. With that system, it would be nice to vary the temperature. That experimental setup we had, we didn't have a way to control the temperature. It was always at room temperature. But that would be something that would... Actually, in the apparatus to measure the birefringence, there was a heating plate on it, but we actually didn't do it. Yeah.
With the separation, could that have anything to do with the angular momentum of the tubes and their specific moment of inertia?
Yeah, maybe it is that the bigger tubes. Well, that's one thing that we thought about also, because these big tubes. So if you imagine this suspension is flowing, the tube's flowing with it, but it only has to move a very little bit, and the velocity gradient's in this direction. So this end feels a bigger push than this end, and it will tend to push it back. With a smaller tube, that has less of an effect. So maybe there's some difference just because of the way the forces the fluid imparts on the tube could be size dependent.
What was the mechanism for the clumping in this case?
The clumping is just because the tubes themselves have an interparticle interaction. If you looked at the interaction potential of the tubes themselves, I don't know if you could. There is somewhat of a van der Waals type interaction between the tubes. It depends a little bit on how bendy they are. But there is a potential well here. So if they get close enough, and of course I should plot this over kVt. So the depth of this well, and that's something with the question on temperature dependence we possibly could investigate. But this guy here is, it's maybe 1 to 2 kVt. It doesn't take a whole lot of shear to break them up, so it's not very deep, but there is an attractive interaction between them. So that's primarily because of the clumping.
Any other questions? All right, let's thank our speaker.